Hello, welcome to this clip about degrees of freedom for the t-test in all its different forms. This is going to be a fairly technical clip, so we're going to have a look at an example first that we will use throughout this clip. For a number of years now, there has been concern in the Netherlands about salt intake of the Dutch people. And when you take in more than 6 milligrams salt per day, that's considered to be bad for your health. So it's interesting, for instance, whether on average, mu is the population mean in this case, people in the Netherlands take in more than 6 milligrams of salt. So you see the null hypothesis here and the alternative hypothesis. The alternative hypothesis being our research hypothesis that people take in too much, more than 6. In order to find out about the population mean mu, we take a random sample of 11 people. We call these observations y1 up to y11, and we will assume that they are from a normal distribution. Actually, this is a normal distribution around the mean mu that we're interested in, with some variance sigma square. To estimate mu, we use the sample mean y bar. Y bar follows a normal distribution as well, around the same mu, but with a smaller variance sigma square over 11. How do you tackle such a problem? Well, early 1900s, this is going to be some history, they did it with a z-test. You can see the test statistic on the slide. And when indeed mu is equal to 6, z will follow a standard normal distribution. So if you look at the standard normal distribution in the gray box, we can look up the number with 5% to the right. That's 1.645. So if the outcome of z exceeds 1.645, at the same time we have a high outcome which points towards the alternative hypothesis, and we have an outcome that has a small probability of occurring under the null hypothesis. So we don't believe the null hypothesis and we will reject. So this is easy. You collect your data, you calculate y bar, and you calculate z. Well, not quite, because we don't know the value of sigma square. What to do? Well, early 1900s, people were not very bothered about this. They simply wiped the problem under the carpet. For instance, eminent statistician Karl Pearson was dealing with fairly large sets of biological data. He simply replaced sigma square by s square, the sample variance. That's not a problem for big samples, but if you have fairly large, small samples, like 11 people, this is a small sample, it's different, because s square and sigma square can be very different. And if, unfortunately, s square is too low, way below sigma square, your t could be too high, and you could reject your null hypothesis for the wrong reasons. So the message is that we should not compare the test statistic, and we call it t now because we are using s square rather than sigma square. We should not compare the test statistic t with a standard normal distribution, but with some other distribution that accounts for the fact that sigma square is being estimated by s square. Now, in 1908, William Seeley Gossett, you see his picture here, came up with the answer: you have to use the t distribution. Gossett was working for Guinness Breweries, and he was regularly confronted with small-scale sets of production data. So with 11 people, the degrees of freedom are all about the arm length, the elbow room that you have for estimating sigma square by s square. And with 11 people, to look at variation, you look at 10 differences. And that's why you have 10 degrees of freedom. Let me explain a bit further. We quantify variation in terms of differences around the mean. That would be mu in this case. That would give you 11 differences, y1 minus mu up to y11 minus mu. But we don't know mu, so we replace it by y bar, the sample mean. But because of this, the 11 differences now add up to 0. So when you know 10 of them, the 11th will automatically follow. It doesn't contain any new information. So there are only 10 differences that you can use to quantify variation, and they are the 10 degrees of freedom. We say that we have lost 1 degree of freedom because we had to replace mu by y bar, which was the reason that all of a sudden these differences added up to 0. So how does it work out? Well, for our 11 data points, we have 10 degrees of freedom. In the gray box, you have the t distribution. We can look up the number with 5% to the right. It's 1.81. So if t exceeds 1.81, we reject the null hypothesis and conclude that Dutch people use too much salt. Note that 1.81 is larger than 1.645 that we used before. Our test has become more severe. We are more cautious because we allow for the fact that S square can be rather different from sigma square. The extra variation is built in the distribution through the degrees of freedom. Now Gosset was corresponding with Sir Ronald Aylmer Fisher. Fisher was something of a statistical genius. Fisher, in contrast to Karl Pearson, actually saw the importance of Gosset's work. And he also realized that Gosset's idea with the t distribution could be used for 2 samples as well. So suppose that we're looking at 2 social classes, and we have random samples of sizes 12 and 17 from these classes, and we're interested in comparing the mean intake mu1 and the mean intake mu2 of these 2 classes. Null hypothesis is that their difference is 0. The alternative hypothesis, the research hypothesis, is that they are not. Fisher discovered that the t distribution still works, but only when the variances in the 2 populations, the 2 social classes, are the same. That's the constant variance assumption. So we have the same variance sigma square for both populations. Sigma square in this case is estimated by SP square, the pooled variance estimator. You can see it in the expression for t over here. We have a sample variance from the one sample, we have a sample variance from the other sample, and we bring the 2 together in the pooled variance estimate. What are the degrees of freedom? Well, we have 12 observations in one sample. That's 12 minus 1 is 11 differences. We have 17 observations in the other sample. That's 17 minus 1 is 16 differences. So in total, we have 27 differences for quantifying sigma square by SP square. So we have 27 degrees of freedom. Actually, the total number of observations is 12 plus 17, 29. And we say that we lose 2 degrees of freedom here because we have to replace mu1 by y bar 1 and mu2 by y bar 2, which is the reason that the differences add up to 0 in the one sample. There we lose 1 degree of freedom. And they also add up in the other sample, and there we lose another degree of freedom. The paired t-test is relatively simple now. Suppose that we have the same random sample of 11 people. And let's say that we measure their intake, and then we leave a brochure that tells them about all the awkward things that could happen to you when you persist in your bad habits with salt intake. And 3 months later, we come back and we measure their salt intake again. And we wonder, did the brochure make any difference? So in this case, it makes sense to look at the intake after the brochure minus the intake before the brochure and look at the difference between them. That will give us 11 changes, D1 up to D11, with a variance sigma d square. And with the one sample t-test applied to these 11 changes, we can actually test whether they are around 0 or not. When they're not, the brochure did have an effect. So in this case, effectively, we apply a one sample t-test on 11 observations, the changes D1 up to D11. So we have 11 minus 1 is 10 degrees of freedom, like we had before in the one sample case. Finally, let's talk about degrees of freedom in simple regression. In the pink box, you have the model. You have an intercept beta 0, a slope beta 1. We have error terms for the variation around the line, epsilon with variance sigma square. You can think of salt intake again, and maybe we want to relate salt intake to age. There are 18 points in the plot, so 18 observations. Let's say that we're interested in a test whether the slope beta 1 is 0 or not. This is an interesting test because if we cannot reject a null hypothesis, we cannot show that our explanatory variable has any predictive power for y. The test statistic is the estimator for the slope beta 1 hat minus 0 divided by the standard error of beta 1 hat. Hidden in this standard error is actually the variance sigma square of the error terms around the line. And again, it will be estimated, this time by the mean square error. So you won't be surprised when I tell you that the degrees of freedom of the t-test are actually the same as the degrees of freedom of the mean square error. So I could proceed with a further explanation based on the ANOVA table with sums of squares, but we'll do it in a slightly different way. We will look at differences again. To quantify variation, to quantify sigma square, we will look at differences between observations y and predictions yi hat, the corresponding points on the line. These are actually the residuals, ei. The residuals are basically estimates for the error terms epsilon I. There are 18 of these residuals, but if you know 16 of them, the last two can be calculated from the others. The reason is that beta 0 and beta 1 have to be estimated, and we lose 2 degrees of freedom again. So the number of degrees of freedom here with 18 observations is 18 minus 2 is 16. Let me explain a bit further. Suppose that we only have 2 observations. You can see them here, the big blue dots. And suppose that the line that you see here is the true line. In that case, we can take the difference between the point on the line and the blue dot. We have 2 distances to the line, and we can use these distances to estimate variation sigma square. That would give us 2 degrees of freedom. The problem is that we don't have the line. We only have the points. So we have to fit a line by least squares. And of course, the fitted line will pass exactly through the points, because that will give us a sum of squares for error, which is 0. You will understand that when the line passes exactly through the points, we cannot say anything about variation around the line. And this is reflected by the fact that the degrees of freedom, n minus 2, are actually 2 minus 2, which is 0. There is no elbow room whatever for estimation of the variance sigma square. So this illustrates that we actually lose 2 degrees of freedom because beta 0 and beta 1 are estimated. Because they are estimated, we have this line passing exactly through the point. When you add another point, a third point, you will have 1 degree of freedom for estimation of sigma square. When you add a fourth point, you have 2 degrees of freedom. So at the end, with n points, you have n minus 2 degrees of freedom. So in summary, we have a one-sample t-test, and the degrees of freedom are n minus 1, where n is the sample size. N minus 1 is the number of differences. For the 2 independent samples t-test, we have n1 minus 1 from the one sample, plus n2 minus 1 from the other sample. In total, the total sample size n1 plus n2 minus 2. We lose 2 degrees of freedom because we estimate mu1 and mu2 by y bar 1 and y bar 2. The pair t-test, basically a one-sample t-test on differences, changes in our case in intake. So you have the number of pairs, the number of changes, minus 1. Simple regression, degrees of freedom are from the mean square error. They are n minus 2. We lose 2 degrees of freedom because of estimation of beta 0 and beta 1. Degrees of freedom are not easy to understand. And since you're looking at this clip, you wanted further understanding. So I hope that this helped. And thanks for your attention, and maybe we'll meet in another clip.